What's happening, folks? Geologist Philip Prince looking out over Southern California. Got LA right there in the very middle of the screen. Like so many parts of the world, you bring in some good digital topography here. This landscape looks really, really cool. Of course, in this part of Southern California, plenty of huge mountain ranges. Got the big San Gabriels back here, Santa Monica Mountains here along the coast. Got smaller things like the Palos Verdes Peninsula there, but LA, it's really flat, which of course is why there is a city there. Worldwide, if you see really big mountain ranges sort of next to or all around a conspicuously flat area in the landscape, that's generally a clue that something is going on there geologically. And of course, in the case of LA, that's no mystery to anybody. Southern California has probably one of the strongest earthquake associations of anywhere on Earth, and a lot, or I guess you could say really all of that stems from the fact that San Andreas Fault's cruising through there, functioning actually as a tectonic plate boundary in this part of the world. And in the case of LA, it's got this bend in it that's actually sort of west or northwest of LA. The movement here along the San Andreas is like that, right? So if you have that bottom and left part of the screen moving away, that's kind of running into the to the bin that we have circled up there. We'll clear everything out, and the end result there is kind of a squeezing effect like that. We'll draw the fault back in there. So with that squeezing, you get this kind of wrinkling and buckling and folding and faulting of the crust. That's what's cranking up the big mountain ranges, but you don't see any of that here in LA. What's up with that? Well, it doesn't mean that it's not going on there, and it's actually an expression of one of the most interesting aspects of Los Angeles geology, which is there's a lot going on that you actually can't see because it's buried underneath sediments at the Earth's surface. So in this video, I'm going to sketch out what's down underneath LA. We'll zoom in on it real close here. Overall goal here is going to be to show you a cutaway. It's going to be on a view kind of like this. Let's see, we'll mark up a couple spots here that we're going to see in the sketch for reference. So we're going to have Santa Monica's here. San Gabriel's, we'll probably get to the point of drawing those in there. Got downtown LA kind of in this neck of the woods. Got the coastline here, Palos Verdes Peninsula, and then of course just a lot of civilization on top of that, sitting on that really sort of undefined flat ground. So the goal here, I guess, is to try to give a sense of how you could visualize geology in a place you can't see it, and how people would do that through actual investigative techniques. And of course, in a place like this, got a lot of people living there. If you have something like earthquake hazard related to faults that you might not be able to see at the surface, be a lot of interest in figuring out where those faults are located and whether or not they actually present some sort of a hazard. So go ahead and jump into that. Go sketch this out in paint. I think this is a pretty cool drawing. It's one that is based off of the huge amount of geologic work that's been done in this part of California. And it is pretty interesting because you have to work in what you see at the ground surface, what you have in the surroundings, and all of this really cool, complex stuff that's really big, but completely down and out of sight in the subsurface. We'll hop out to paint here. Hang on just a minute. Okay, so what's actually hanging out down underneath that mostly flat LA basin surface? I'm gonna diagram it out here. I got to leave myself plenty of room at the top there so we can make this kind of a 3D thing out into the distance. Okay, so what's actually hanging out underneath that mostly flat LA basin surface? Well, let's get it diagrammed out here. I gotta try to leave myself some room at the top. Just take this out into the distance for the kind of the 3D block look, but diagram like this not so bad to mess with because you don't have a whole lot to do on the surface of the earth there in terms of topography, at least in this area. Give ourselves a coastline there. And we'll try to set up the land surface here and then build in the geology down underneath it. That'll be the land surface. Got our ocean over here. Give myself a little bit of ocean bottom detail here as well. Mostly shallow water, but we'll have the very start of some of these canyons that are off the coast and kind of going out into deeper water there. Cool. Features on the surface, well, they don't look very big, and yeah, there's a reason for that. Geologic structures like we're about to sketch out here are really, really, really huge compared to the topography that you actually see on the surface of the land. And as I draft in the Santa Monica Mountains here, they should look pretty small compared to the overall layout of the diagram. So if that's going all right, probably going to be okay here in terms of an overall kind of general physical scaling of this sketch. Add a little bit more topography here. And it should be in good shape to start doing some subsurface. I guess we can go ahead and put downtown LA on here real quick, just as a good frame of reference. And then we'll have Beverly Hills kind of area down here at the foot of the Santa Monica as well. Put a Santa Monica pier out there and actually add a few breakers here on the coastline. I don't know if anybody will be able to see that. I think it's nice. All right, so what's under the ground? We're actually going to start that off from just these few little bumps there on the surface that are just behind LA with respect to the coastline. Have something like this going on here. That should work out pretty well. Actually, I think I can make that even a little bit thicker. Cool. All right. Very good. So what I'm trying to draw in here with a reasonable level of smoothness. Make that a little bit deeper. A lot of erases and backups here, but that's all right. We don't get it worked out. Are these overall geologic structures that sit down underneath that flat basin surface and ultimately affect both the continental crust, what we call like the basement geology, as well as the sedimentary layers on top of it. As a final touch here, we'll do this one with the pencil. Going to need another kind of little geologic division that's going to offset some of our youngest sedimentary layers up there. And at this point, we can probably start filling in a few colors here. Had a couple more faults there. So that gray is going to be our basement rock. That's our deeper rock. Metamorphic rock in many cases, but it's essentially the like the crust on which these sedimentary layers have been deposited in the geologic past. On top of that, have our sedimentary layers there. We use a purple for that just as something that kind of stands out as a color, and then we'll make a slightly lighter shade of purple for some of those slightly younger sedimentary layers. And then the uppermost ones here, we'll give those kind of a totally different color. Do something like that. We'll see if we can set that apart from what you see on the ground. Should be enough difference there. Okay, cool. So here's our geologic layout down under the surface, and we've already drawn in the potentially kind of hazardous thing that's 25,000 feet under LA, and that is that fault right there. That is a thrust fault. So the movement that it's developed over time is like that. So it's pushing rock layers up as a result of that squeezing along the bend in the San Andreas Fault that we talked about. And if we scaled that out, indeed, if you drilled straight down about 25,000 feet or something like that underneath downtown LA, you would hit that fault. The fault doesn't come anywhere to the ground surface. It's called a blind fault for that reason. And it's one that's kind of interesting because it absolutely could produce earthquakes. For example, if slippage occurred over this section of fault right here is just an example that is kind of going up in that ramp type of shape there. That could give you a pretty good sized earthquake. It's right underneath LA, and those shock waves are going to go right up into these shallow sediment layers here that tend to not stand up to that particularly well. How big of an earthquake could you have in a place like this? In the magnitude sixes or sevens, there's a lot of study of that. You see a range of values, but it all comes down to how big of an area of fault or faults could slip at the same time. And the bigger estimates you see are in the magnitude 7 range. Now, this isn't the so-called big one. That's over on the San Andreas itself. But because of the location of the fault that we've highlighted here and others underneath the LA basin and their potential, they're absolutely worth knowing about. How do you know about them if they're down there and out of sight? That's kind of a difficult question. We'll add a little bit more detail in here. Got all kinds of faults that link up in all kinds of strange geometries. This is a very simplified geology in the sense that those purple sedimentary layers are in some locations much thicker than in other layers. The crust here was broken and stretched before it got squeezed back together. This is again very much simplified just to catch the overall visual of the effects of the squeezing. You can look at what's on the ground surface, so you can look at these tilted layers that are poking up on the surface here. Those give you some idea that something is going on down deep under there, and the fact that that tilted area is pretty wide shows you that a pretty thick sequence of rock there is being deformed to produce that tilted shape. Another thing that you can do, at least to explore the shape of the tops of some of these structures, is drill for oil. There's plenty of that in the LA basin. The lower parts of the sedimentary layer sequence here have very good oil source rock. When they get buried deeply enough under the appropriate conditions of temperature and pressure, they produce oil, and oil tries to migrate up as far as it can. Sometimes it gets stuck in pockets of sandstone that are nice and porous and have space to actually hold the oil in the rock. A lot of times, those good storage spots, what we call traps, are in the tops of these folds, like you see here. And you can come along and drill down and get that stuff out of there and start to get a sense of at least what some of that sedimentary layer geology looks like. And it's all kinds of wrinkled and folded up, which is again evidence that there's plenty of geologic structure here. It's just down and out of sight. Through that search for oil, people actually produce what we call seismic surveys, where they send big shock waves down from the ground surface. Those shock waves bounce off of these geologic structures down underground. You read those at the surface, interpret the data, and you actually get sort of almost like a sonogram type of picture of what's down underneath the earth. So there's a variety of ways of exploring what's down there. There's not really consensus on what's down there, but at the very least, this part of the diagram, again, that's down like right underneath LA, that is widely agreed upon between geologists. The way I've done this diagram is heavily modeled on work by Thomas Davis and Namson. There's a website called Davis-Namson Geologist that has a lot of really cool publicly downloadable material that shows you what real measured geologic work in an area like this looks like. Geology at the end of the day is a lot more like engineering or architecture, particularly when you're dealing with structure. And that website actually shows you what products related to that approach really look like. So it's not just this thing's old, this thing came from deep in the earth. The geometry behind it goes well beyond that. Really cool site to check out. But at the end of the day, despite drilling, seismic investigation, whatever, this fault down here just kind of goes out there and stops somewhere, and nobody really knows for sure what its exact geometry is. But rest assured that there are people that are plenty interested in what might happen if it slipped along a length like that. Another interesting way of looking at what's down under the ground is to produce physical models. Geologists have done this for over a century. You do it with loose granular materials, which act like scaled down rock layers. You're basically making like a 1/1 millionth scale model. Put one on the screen right now. Shaking out these layers of dry sand, have to have different colors so you can see contrast, and actually going to squeeze those along kind of a bend, and that's basically reproducing like this bend in the San Andreas setting, and you can see that kind of wrinkling and buckling effect as the layers get squeezed. What does the end result of that look like? Put that on the screen right now. If you take a model like this and cut it open, it produces pretty recognizable structures, particularly if you were to focus in on that area of the model. The resemblance should come through there. Actually got it right here in real life. So you can harden these things by soaking them in gelatin and dry them out and keep them as kind of a physical reference. So that's another way of trying to solve geologic mysteries like this. But ultimately, if you see a mountain range with a really flat area nearby and an area that's known to have earthquakes, there's all kinds of crazy stuff down under that sedimentary basin. It's the interpretation of it that ultimately presents the challenge. And I guess as a final thought, since we're here, we might stretch this thing out all the way to the San Andreas. So if we were to move this over here, we're going to cut that side of the model off. This should go fairly smoothly. Take ourselves out to some slightly bigger mountains like that. Still not nearly as large as the overall size of our geologic structures there. We'll fill in the ground surface there. We can just fill all that in as the basement rock as well. We'll stretch our fault over there all the way back here to the edge, and we'll have the vertical edge of this model. We'll say that is the San Andreas fault right there. All of these other faults are sort of linking to that. Basically, they're associated with that system in one way or another. And in particular, have this big thrust at the base of the San Gabriel Mountains there that's kind of pushing up that area of much higher topography. We'll put a little bit of white snow cover up on top of them there. So that's the overall picture, and the big idea is basically again like pushing away from the San Andreas as a result of that really conspicuous kink in it right there. Guess I could probably improve that just a little bit by adding something over here to show you that the San Andreas is cutting through the crust, and we've just kind of cut our diagram off there on the edge. That I ought to work it out right there. Very nice, complete. So kind of a cool system, a place that combines that kind of strike slip motion with elements of the squeezing. And within the LA basin, there are faults that are both thrust faults that are pushing rock up, like you see here, and also strike slip faults that are causing the geology to slide side by side. And as we speak, people are trying to better understand this system, just in hopes of keeping people aware of at least the earthquake potential in a place like this where you can't actually see the faults that are likely to slip down at depth and cause an earthquake. So step back to the maps here real quick, take a look at a couple more things, call it a day. Hang on just a minute. Okay, so that's the big idea of what's down underneath this generally flat and really, really heavily developed LA basin. Some of the areas around here, you basically have evidence at the surface of the underground geologic activity. Puente Hills here, sort of behind Whittier, would be one example. The Palos Verdes Peninsula here out there on the coast would be another one. Things like tar pits, La Brea tar pits. That's been a common question on this channel. Why would you have tar pits? Well, we can zoom in on the diagram here real quick and explain that one. If you had fault development actually cutting through one of these areas where oil is trapped, that would allow the oil to migrate up that fault and actually end up coming out as tarry material on the ground surface. So the fact that there are tar pits here is every bit a reflection of, number one, the presence of petroleum type stuff underground, and number two, faults breaking through those traps and actually allowing that material to migrate up to the surface. If you wanted to adjust that diagram, to account for something like the Palos Verdes Peninsula here, you just come over here on the left-hand side, and basically you would just push some of these purple layers up just a little bit further, to where they actually make a bigger hump coming out of the ground there. This isn't a perfect replication of what folks interpret to be the geologic style there, but at the end of the day, that Palos Verdes Peninsula with that big kind of humpbacked elevated hill or small mountain there is just, it's just the top of a geologic fold like we've been drawing in this diagram. So you can find plenty of evidence all around here for these geologic processes that are going on down under the surface and out of sight, but really understanding them at detail is always going to be tough. And there's no better example of that than what's right in the middle of the screen right now. San Fernando Valley, the Northridge earthquake in 1994 was straight down underneath where the hand is roughly. And it was about 60,000 feet deep. It was about 18 kilometers under the ground surface. And it occurred on a thrust fault that was actually pushing rock away from us. It was pushing sort of towards the north, totally down under the surface. Another one of these blind faults like we talked about in the diagram here. And one that of course produced significant effect is the magnitude sixes, but very damaging right down underneath such a heavily developed area. I guess we could actually take a shot here at laying that out. We can do this one just as kind of a line drawing, but we had the coastline, Santa Monica Mountains, San Fernando Valley. In the case of Northridge, a similar type of thing, have the coastline right there. See how fast we can do this one. And another one of these big kind of thrust structures here that's pushing layers kind of up and over each other. Drawn out here. And in the case of Northridge, we should make it a different color, one that we can see. The earthquake was down on a fault positioned like that. So with the squeezing here, squeezing together, and it's almost like a block of rock is being popped upward by rock. I mean, of course, like the entirety of the Earth's upper crust there. Like lay out some mountains real quickly here, and you'd have Northridge out in the valley like that, with the kind of waves kind of coming up like that. So it's very much a similar idea, and one that has highlighted the importance of trying to understand the geology down deep there. So, hope you found this video interesting. I'm fascinated by this area, very different from what we have here on the East Coast, and like so many other active tectonic places around the world. I imagine that living there, I don't know, this is like a part of your daily life, even though it's down and out of sight and hard to see. So it's an interesting way to think about, at least for me, about living with geology impacting your life in a totally different way than it does here in the Appalachians on the East Coast. So I hope you enjoyed this video. Hope you check out the next one when it comes along.